Dear viewers, I welcome you all for this next third episode of infrared spectroscopy, where we are trying to discuss the number of fundamental vibrations and the mode of vibrations. And myself, Dr. Girish Hampanava, Assistant Professor, Department of Pharmaceutical Chemistry, KLA College of Pharmacy, Vidyanagar, Hubli, would like to engage you guys with these particular two topics, that is number of fundamental vibrations and modes of vibrations. So before we go for understanding the number of fundamental vibrations, we need to understand some basic things like degrees of freedom. And there are 3 degrees of freedom. And what are those degrees of freedom? For example, translational, rotational, and vibrational uh, degrees of freedom. And we also need to understand how we end up having the kind of vibrations which a molecule is supposed to possess when it is a linear molecule, when it is a non-linear molecule, or so on and so forth. We are considering some very important things in this particular discussion. So in order to understand the number of fundamental vibrations, so what we mean by the fundamental vibrations. So before we go into very depth of this fundamental vibrations, I would like to simply take you through the understanding of the fundamental vibrations before we dive into deep with this particular topic. So when we see any IR spectrum of any given organic molecule, that may show so many peaks or absorption bands, and those many absorption bands make that whole spectrum so complex that whole absorption bands or whole of those absorption bands which appear in that particular IR spectrum, that is because of the vibrations of so many functional groups or so many atoms which are attached to each other. So molecule as a whole experiences the vibrational absorption bands. So it tends to show so many absorption bands in an IR absorption spectrum. So how do you account or how do you end up having the number of bands which corresponds to corresponding to a certain fraction of those molecules? How do we end up identifying so how many vibrational possibilities are there in a given molecule? So all of those we can understand by something called as degrees of freedom. So the number of these bands corresponds to the number of fundamental vibrations in a molecules, and how many number of fundamental vibrations that can be calculated from degrees of freedom of a molecule. So when I say degrees of freedom of a molecule, it is nothing but any molecule, whether it is a monatomic, diatomic, or triatomic, so on and so forth, it has certain degrees of freedom. Degrees of freedom in the sense when an atom is either for example, monoatomic atom, if it is left out in a space, okay, so it has 3 degrees of freedom. What we mean by 3 degrees of freedom is it can move on 3 particular axes, that is x, y, and z. It has 3 degrees of free movement in a space. So we call that particular thing as degrees of freedom for any given molecule. So when a molecule comprises n different atoms, so if I have a molecule which has n number of atoms in it, we can say that particular molecule has 3n degrees of freedom. I mean to say n is nothing but the number of atoms that a molecule comprises of. So when we have those degrees of freedom, a molecule may possess those many number of possibilities, whether it is translational, rotational, or vibrational kind of motions. So if I have a non-linear molecule, if my molecule is non-linear, then 3 of these degrees of freedom are rotational, and 3 of these are translational, and the remaining, that is 3n minus 6, we apply this 3n minus 6 to non-linear molecules, and for a linear molecule we apply 3n minus 5 degrees of freedom. So in this particular case, I have a non-linear molecule which has 3n minus 6 degrees of freedom, among which 3 degrees of freedom are the translational, and the 3 degrees are rotational, and the remaining, how many are remaining now? If I have a non-linear molecule, I need to substitute how many atoms, then multiply with 3, then deduct 6 from that. The remaining would be the fundamental vibrations. Okay, down the lane, I have one particular chart where we will understand for non-linear molecules, for this particular formula, how many degrees of freedom are available each for translational, rotational, and vibrational. Similarly, if I have a linear molecule, only 2 degrees of freedom are rotational, because the rotation of axis or the rotation about its axis of linearity does not change the position of atoms, and 3 are translational, and the remaining are, when we substitute n in this formula, whatever are remaining after we deduct 2 for rotational and 3 for translational, whatever are remaining, those many remaining are nothing but the vibrational degrees of freedom or the fundamental vibrations for that particular molecule. So that is what we mean by fundamental vibrations for a given molecule. So when molecules tend to become more complex, and it tends to have more bonds, more number of bonds, and different types of atoms, so they may possess different types of vibrations, and these vibrations are broadly categorized into 2 types. The first one is the stretching and the bending vibrations. So when we go after this, when we finish this number of fundamental vibrations topic, we go for the next topic, which is the modes of vibrations. In that, we will be discussing these 2, stretching and bending vibrations. That is when molecules tend to become more complex and it has more number of atoms and more number of bonds. So the vibrational motions or the vibrational observations or the fundamental vibrations what we observe from these complex molecules, they are broadly categorized into these 2 kind of vibrations, that is stretching and bending. We'll go into very detail in modes of vibration about this stretching and bending vibrations. So just to summarize what I have said just now, polyatomic, I mean to say so many atoms in a molecule may exhibit more than one fundamental vibration absorption band. That's why any given IR spectra is very complex, and it is not that simple, because all those atoms which that particular molecule possesses, all those atoms which are interlinked by a certain types of bonds, all these atoms tend to show some or the other absorption. That's why the fundamental vibrations become more complex, and IR spectra as a whole tends to become more complex. The number of these fundamental vibrations, fundamental bands, is related to the degrees of freedom, as I've just now mentioned in the previous slide. So when an atom combines to form a molecule, number of degrees of freedom are lost. That is, the molecule has total 3 degrees of freedom, and I said just now 3n minus 5 and 3n minus 6. N is nothing but the number of atoms. So when I say 3 degrees of freedom, it is nothing but the sum of translational, rotational, and vibrational. So for a linear molecule, it is 3n minus 5 formula, and for non-linear molecule, the vibrational degrees of freedom is 3n minus 6. We need to remember this 2 things. For linear, it is 3n minus 5, and for non-linear, it is 3n minus 6 degrees of freedom. So when I say there are 3 degrees of freedom, one is translational, rotational, and vibrational. How is it, how we try to visualize or tend to imagine those kind of transition or those kind of degrees of freedom is like, we'll go through each of these. For example, in the translational, the movement of the entire molecule with the position of the atoms relative to each other remain fixed. I mean to say, if consider a diatomic molecule, I mean to say one atom joined to the other atom by a single bond. If that is the case, then if we consider a translational motion for that particular molecule, then the moment of the entire molecule with the position of the atoms relative to each other. I mean to say, when I'm considering 2 atoms linked by a bond, the relative position between these 2 atoms is fixed, and if it is to go the translational motion, then it has 3 degrees of translation freedom. I mean to say, the whole molecule, diatomic molecule, it may go either into x-axis, it may go into y-axis, or it may go into the z-axis. So we call it has 3 degrees of translational freedom. In the next slide, I will be taking certain examples where the visualization becomes very easy. Coming to the next kind of degrees of freedom, that is rotational transitions. So we try to imagine the rotation of the molecules across the bonds. So the interatomic distance will not change here and it remains constant, but the entire molecule rotates. With respect to three mutually perpendicular axes, three rotational freedom for non-linear and two rotational freedom for linear. I have taken two different examples in the coming slides where we understand why the non-linear molecule has three rotational freedom and how it has a three rotational freedom and how a linear molecule has a two rotational degrees of freedom. So any molecule for that matter has 3 degrees of translational motion, and with respect to rotational, if the molecule is non-linear, it has only 3 rotational degrees of freedom. If it is a linear molecule, it has only 2 rotational degrees of freedom. That we should keep in our mind. And all the molecules will have 3 degrees of translation freedom. Coming to the vibrational, this is quite variable. I mean to say, this kind of vibrations, degrees of freedom, it changes, and the number is quite dependent on the formula which we use, which is 3n minus 5 and 3n minus 6. I'll come to this table just now. So vibrationals or vibrations, during the vibrations, the relative positions of the atom change. I mean to say, when just imagine the same diatomic molecule, one atom joined to the other atom. When we imagine the vibration across the single bond of these two atoms, then the relative positions, because of the vibration, they may come towards each other. The atoms may come towards each other, or they may travel away from each other. I mean to say, the relative position of these atoms will change, and the average position and the orientation of the molecule still remains fixed. I mean to say, if it is a big molecule, the atoms may vibrate, but still it remain or those atoms remain fixed to the molecule at that particular point of molecule where it is attached to another atom. So summarizing this whole thing here in this table, considering the degrees of freedom for a linear and a non-linear molecule, what I have just now discussed, with respect to the translational motion, I said for all the molecules it has 3 degrees of freedom or 3 degrees of translation freedom. Any molecule you take, it has 3 degrees of translational motion. Coming to the second degree of freedom, that is rotational. In case of linear molecule, where I just now mentioned, here you can see there are 2 rotational freedoms. I mean to say, we have only 2 rotational degrees of freedom for a linear molecule, and if it is a non-linear molecule, we have 3 degrees of freedom in case of rotational motions. And whatever are remaining, I mean to say, if we have a number of atoms, which is nothing but the n, when you substitute in this particular formula, that is 3n minus 5 for a linear molecule, the remaining degrees of freedom, those will be accounted for vibrational. I mean to say, if I have three atoms, what I do is I substitute n is equal to 3, 3 3s are 9, 9 minus 5 is nothing but 4. Then I mean to say 4 vibrational degrees of freedom are possible for a triatomic linear molecule. That is how we calculate 5 vibrational degrees of freedom, and among that 5 you can see 3 plus 2 are already occupied. So there are that is how we calculate these degrees of freedom. So in total it is, if you substitute 3n, I have 9 degrees of freedom in total. So if I take out 5, the remaining 4 will be the vibrational. So that is how we calculate the vibrational degrees of freedom. See, if you add this 3 plus 2, it will be 5, and 3 plus 3, it will be 6. That is how they calculate this vibrational degrees of freedom by this formula. So just if you remember this 3n minus 5, this top 2 should make 5, and if it is 3n minus 6, the top 2 should make 6. So that is how we can remember the vibrational degrees of freedom for linear and non-linear molecule. So if you take a molecule as a whole, it is 3n degrees for each linear and non-linear molecule. So coming to, let me take a linear diatomic molecule. So I have taken this linear molecule now. When I tell diatomic, I have n is equal to 2, 3 2s are 6, 6 minus 5 is 1. So 1 vibrational is possible, and 3 translational, 2 rotational, and 1 vibrational are possible. So that is how I have counted here. 3 translational, 2 rotational, and 1 vibration is possible, which is nothing but the fundamental vibrations. This we consider as a fundamental vibrations. So just by applying this particular formula, that is 3n minus 5, we can finally calculate the number of fundamental vibrations in a given molecule. I have taken nitrogen, which is a linear diatomic molecule. It is nothing but 3n minus 5 formula, where 3 times 2 is 6, minus 5 is 1. 1 is nothing but those many vibrational degrees of freedom are possible. So if I go with this translational motion, this nitrogen, which is a diatomic molecule which is attached to a single bond, may move in either z-axis, it may move in y-axis, or it may move in the x-axis. So it has 3 degrees of freedom. Any molecule for that matter as a whole has 3 degrees of freedom, which is the translation degrees of freedom. Okay, so any molecule, there are 3 degrees of freedom for translation vibrations. So coming to the rotational, since it is a linear, 2 rotational motions are possible. So it is a diatom. Either it can tend to move this way, or either it can tend to I think you can see this square and see this square, where the orientation of this square box is quite different. That is how it says the axis in which these atoms can rotate. You can see the axis is oriented in this way, and the axis is oriented in this way. I mean to say in either y-axis or in z-axis. Coming to the vibrational, you can see these 2 arrows. Either these 2 atoms can come towards each other, if you see these 2 arrows, and they either can go away from each other if you see these 2 arrows. So there are totally 3 translational, 2 rotational, and 1 vibrational degrees of freedom for this linear diatomic molecule. Similarly, it is a linear triatomic molecule. When I say linear, it is 3n minus 5. I'll just try to show this. Linear molecule, it is 3n minus 5. So it is a triatomic molecule now. N is equal to 3. 3 is 9. 9 minus 5 is nothing but 4. 4 is nothing but the vibrational degrees of freedom. We have 1, 2, 3, and 4. We can see the 4 degrees of vibrational fundamental vibrations for this carbon dioxide, which is a linear triatomic molecule. So if you see, again, 3 degrees of translational motion, 2 degrees of rotational motions, and 4 degrees of vibrational motions. So the same understanding for nitrogen, it applies the same to this carbon dioxide for translational and rotational. But let me explain you this vibrational kind of fundamental vibrations. The first we have symmetric, and the second we have asymmetric stretch. Okay, we talk about stretch and bend in 2 different things now. So when we have these fundamental vibrations, they are broadly classified into 2 things, either the stretching vibrations or the bending vibrations. Just imagine the previous discussion what we had in the second episode with respect to the Hooke's law. Imagine this to be a spring, this bond to be a spring, where it is connected to one atom, and at the other end it is connected to the other atom. So if you imagine this bond as a spring, it could either be stretched or it could be either bent. So there are only 2 possibilities across this bonds, and either it can stretch or either it can bend. So if you see this symmetric stretch, I would like to draw your attention to these 2 arrows. Symmetric stretch is where these 2 atoms, which are represented in red color, the carbon and 2 oxygen atoms, these oxygen atoms will come towards carbon and they move away from the carbon simultaneously. That we call it as symmetric stretch. They come together, both oxygen towards carbon, and they move away together from this particular central carbon atom. We call this as symmetric stretch. And antisymmetric or asymmetric is when one oxygen atom is coming towards, the other one will move away. Okay, so that is what the arrow is representing here. this oxygen is moving towards the carbon, whereas this oxygen is moving away from this particular carbon. So this becomes a symmetric stretch. Okay. Similarly, if this is moving away, this oxygen is moving towards this carbon. Okay, I would like to bring your attention to this set of arrows, which will help you in understanding this kind of asymmetric stretch. These were two different symmetric and asymmetric stretching vibrations, and we have two different bending vibrations, also known as deformations. Bending vibrations, we also call them as deformations. And this oxygen, just look onto those only top arrows. This oxygen atom may bend towards left, whereas this oxygen atom can also bend towards left, whereas this carbon will bend towards right. It means oxygen and oxygen moving towards my left. And in the second possibility, one oxygen is moving to the right and the other oxygen is also moving towards right, whereas the carbon is moving towards the left. I mean to say, it is vice versa for the initial understanding. Similarly, this oxygen may move towards left and this oxygen may move towards left, whereas this carbon may move towards right. Okay, so this is a kind of bending vibrations which we will understand in very detail when we actually go into the modes of vibrations. Okay, I will take one more example for a non-linear triatomic molecule. When I say it is non-linear, let me take back to this particular slide. When I say it is non-linear, it is 3n minus 6 formula. So it is triatomic molecule. 3 times 3, it is 9. 9 minus 6 is nothing but 3. It is 3 translational, 3 rotational and 3 vibrational degrees of freedom. Okay, you can see 3 translational, 3 rotational and 3 vibrational degrees of freedom for this water, which is a non-linear triatomic molecule. Again, this water molecule as a whole can move in z-axis, in y-axis or in x-axis. It can rotate either like this or either like this or either like this. I request you to imagine because I cannot actually show this rotations on this one-dimensional screen. Okay, so again, considering the vibrational degrees of freedom, we have 3 vibrational degrees of freedom. It could be a symmetric stretch and asymmetric, and it is also a symmetric bending deformation where these two are stretching and this is a sort of bending kind of vibrations. So this was about the 3n minus 5 and 3n minus 6 formula, which was for linear and non-linear atomic molecules respectively. So I have this particular table here which helps us to understand with respect to a kind of molecule we have and what is the number of atoms they have and the kind of degrees of freedom they possess and the kind of modes of vibrations they possess. So it is a monoatomic molecule. It has n is equal to 1 and it is 3n, where when n is equal to 1, the total degrees of freedom we have is 3. And we know that all the molecules have 3 translation motions. So the remaining 2 will become 0 because the 3 degrees of freedom have already been occupied by translation. So if the molecule is diatomic, n is equal to 2, and if it is 3n, then it is 3 times 2 is 6. We have 3 translational, and we consider it to be a linear molecule. It is 2 rotational, and the remaining is 1 vibrational. So it is triatomic linear. It is again 3n minus 5 formula. So 3n, 3, 3, 9. 9 minus 5, remaining is 4, and we have 4 vibrational degrees of freedom, and translational is 3, and remaining 2 would be the rotational. So non-linear triatomic molecule, water is the best example we just now discussed. It again has 3 degrees, n is equal to 3, it has 9 degrees of freedom, 3 is already translational, 3 rotational and 3 vibrational because it is 3n minus 6 formula. So I hope this was quite convincing and you could understand more about these degrees of freedom. So it has been observed that the theoretical number of fundamental vibrations, what we discussed, what we calculated was the theoretical number of vibrations what a molecule should possess. For example, H2O should possess 3 vibrations, and carbon dioxide should possess 4 vibrations, and diatomic molecule HCl should possess 1 vibrational, and they should not possess any vibrational rotations. So these all are theoretical considerations. But if you consider practically, the theoretical number of fundamental vibrations are never observed or never obtained, because we have some reasons why we cannot observe all the theoretical calculations or theoretical number of fundamental vibrations, because we have some reasons, because some vibrations or some fundamental vibrations may fall out of the region under investigation. So if I am looking into 400 to 4000 centimeter inverse, which is the mid-IR region, some of these fundamental vibrations may fall out of this mid-IR region. That's why we fail to recognize these fundamental vibrations. And sometimes they are too weak to be observed as a peak or a band. So these fundamental vibrations are so weak, they cannot be distinguished as a peak. So they are too weak to be observed as a bands. And the other possibility is these fundamental vibrations, they may happen to be so close, or they sometimes overlap with or the other bands, and they simply degenerate or they disappear, and we cannot identify them as a fundamental vibrations. And sometimes some vibrational fundamental vibrations do not appear simply because they require a change in dipole moment, which may not happen. For example, the carbon dioxide, where the symmetric stretch will possibly do not show any vibrational or fundamental vibrations, because there is no change in dipole moment that is visible in that particular symmetric stretch of carbon dioxide. So there is one more possibility why we do not observe all the fundamental vibrations, is because they may appear as some additional bands called as combination bands or difference bands or overtones. Thus, due to this, a large number of bands will be observed as compared to a theoretical number. So we may tend to lose so many peaks or bands, and practically the theoretically calculated peaks may not be visible, or sometimes we tend to lose them because they may are overlapping, they are simply disappearing, or they may fall outside the region of investigations. So we need to understand what are these combination bands, difference bands, and overtones. If there are two fundamental bands, for example, I have two fundamental bands like X and Y, then the additional bands can be expected at 2 times this fundamental band, that is X, and 2 times the distance of this fundamental band, which is nothing but Y. We call, in that particular case, we call them as overtones. For example, if it is a band at 1600, if you see one more peak at 3200, then we call it as an overtone. If it is one band at 800 and there is one more additional small band at 1600, that 1600 band we call it as a overtone. So it is simply times 2 the observed fundamental band. We call those kind of bands as overtones. And if it is the sum of two fundamental bands, or the twice, I mean to say x plus y or x plus 2y or 2x plus y, we call these kind of bands as the combination bands. I request you to understand or take this kind of 2 times the x or 2 times the y, so that you can imagine and understand what we mean by the combination bands. If it is the difference like this, x minus y or x minus 2y or 2y minus x, these kind of bands, wherever they appear, once after substituting the values or the wave numbers for this x and y into these particular formulas, wherever we get those peaks or bands, we call them as difference bands. And one thing is to be noted, that is, these additional bands in general are usually very less intense, like 10 to 100 times less intense than the fundamental bands, and sometimes there are high possibility that we lose them during the observations. And one more thing is, these absorption bands in the near infrared region, I mean to say these additional bands, what I was talking about so far, these additional bands, what happens is they fall outside the mid-IR region, or rather they may fall in the near infrared region. For example, absorption bands in the near infrared regions are the result of combination and overtone bands from the fundamental vibrations which are seen in the mid-IR region. So if you are observing the fundamental vibrations in the mid-IR region, their combination or overtones or additional bands may appear in near infrared region, which is nothing but the much more energetic region when compared to the mid-IR region. So possibly we are not interested in near infrared, rather we are interested in mid-IR region. We tend to lose those important observations because we are not considering going beyond 4000 centimeter inverse, which is nothing but the near infrared region. The overtone and combination bands are, as I mentioned, 10 to times less intense than the fundamental bands in the mid-IR region. If they are happening, they are very less intense, and possibly we may lose or they are very subtle to be seen as a peaks or bands. Difference in spectra are often subtle, I mean to say very difficult to recognize, requiring the training of analysts to recognize these particular differences. So it only comes with experience in order to understand or identify these overtones, combination bands, and the difference bands, and that in the other way become a confirmatory. We can confirm just by looking on to those particular regions. If you see, if there is an additional peak, then we can confirm, okay, that is the peak what I was intending. If it was a particular vibration, for example, if it was a CH, NH, or OH, it is to have some additional combination or overtone bands, which is in other ways suffices as an evidence so that you can go and see them. And if you have them, then it is a very confirmation that these particular vibrations are happening in your molecule. So I have an example here where I have taken it from a particular research paper which is from a journal Polymers and Rubbers, authored by Norbert and Thomas, and it is a copyright protected image, so I thought to acknowledge John Wiley and Sons. And you can see here 400 to 4000 is my mid-IR region. Here is the end of my mid-IR region. I'm trying to point it here. I am very much interested after this 4000 towards 400, but beyond this 4000 it is the near infrared region where we are losing very important, I mean to say, some of the additional peaks like the combination bands and the overtone bands, which are happening much above this 4000 wave number region, which is nothing but the near infrared region. So that is how the overtones or the combination bands, they fall out of the mid-IR region, and they tend to be visible in the near infrared region. That is how we need to have a broad understanding of identifying these bonds out of the region what we are actually looking, that is the mid-IR region. So with that, we will now go for the modes of vibrations, the fundamental modes of vibrations, the vibrational degrees of freedom, what we understood, how they are vibrating. I said there are two modes of vibrations, which is the stretching and bending. We need to understand those modes of vibration, and it is a very important concept which all should be knowing. So I said there are two fundamental vibrations, one is stretching and the other one is bending. Stretching is further categorized as symmetric stretch and asymmetric stretch. Bending is further categorized as in-plane bending or deformation. Bending can also be called as deformation, in-plane bending, and out-of-plane bending or deformation. So in plane we have two subtypes. The first one is scissoring and the second one is rocking. And out of plane is the first one we have the twisting, and the second one is wagging. So I have some animations in the coming slides so that we can understand very easily this set of fundamental vibrations. Coming to the stretching, we have symmetric and asymmetric. So this is the symmetric, where the two atoms will, these two yellow atoms will move towards the red atom simultaneously or move away from this red atom simultaneously. We call them as a symmetric stretch. You can see here in this particular animation, which is again a copyright image which has been taken from source, and it has been acknowledged here. And you can see these two atoms move towards the central atom simultaneously and move away simultaneously. So we call this as a symmetric stretch. And here is an example of asymmetric stretch. Why? There is no symmetry in their movement, because one is moving out towards and the other one is moving away simultaneously. You can see if this moves, this atom moves in, this atom moves out. That is, there is no symmetry in the movement. That's why we call this as asymmetric stretch. Coming to the bending vibrations, as I mentioned, in plane, out of plane, I have scissoring and rocking as in plane bending. Scissoring is nothing but if these two yellow atoms move towards each other and if they are still in the plane of vibration, we call them as in plane. Okay, if they are still in the plane of the paper or the screen, we call them as scissoring. Here you can see the two atoms are scissoring and they are coming towards each other and moving away from each other. And since they are on the same plane, we categorize them as in plane deformation. The next one is rocking. These two atoms will move in the same directions. We call them as rocking. You can see these two atoms moving in the same direction and coming back in the same direction, but they are still in plane. I mean to say on the plane. So we call them as in plane deformations. We have scissoring and rocking for this. And out of plane deformation, we have twisting and wagging. This particular example here, the yellow atoms, one I have denoted as plus, the other one I have denoted as minus. That is simply to denote plus is towards me, minus is away from me. Okay, so twisting is nothing but one atom coming towards me and one atom moving away from me. It is not in the plane, it is moving, or these atoms are moving out of the plane. So we call them as out of plane deformation. Here, these two atoms are moving towards me. We call them as wagging, and this we call it as twisting. So the bending vibrations we have in plane and out of plane, scissoring, rocking, which are in plane, twisting and wagging is out of plane bending vibrations. So we have very different modes of vibrations, and I have got this animation from chemlibretext.org. Very important. The previous discussion, what we had just now, we can imagine in terms of the CH bond. So it is asymmetric. The first one is asymmetric, and the second one is symmetric, stretching vibrations, and these two are stretching, and the rest one are the bending. Scissoring and rocking are in plane. You can see this is scissoring and this is rocking, both are in plane. And twisting and wagging, you can see the change in the bond shapes and the orientations. The first one is twisting and the second one is wagging. This is out of plane deformities or bending vibrations. So this was about the modes of vibrations and the fundamental vibrations. So with this, I thank you here, and we would like to in the next session I would like to discuss more about the factors that influence the vibrational frequencies, but in this episode it will be only this much. Thank you very much for your patience and listening.